Hello everyone, my name is Suvir Mirchandani, and in this talk we introduce ELA, Exploration through Learned Language Abstraction, a method for guiding exploration in language-conditioned reinforcement learning agents. This is joint work with Karamcheti and Dorsa Sadigh. A goal for human-AI collaboration is to build agents that can perform tasks specified in language. A critical aspect of language is its principle of abstraction. A simple statement, like, please get me an apple, abstracts over lower-level components, like go to the table, pick up an apple, and drive to me. In this work, our aim is to leverage these abstractions to amplify the sample efficiency of systems like this one, which learn to convert commands into actions. This problem is called instruction following, and it's commonly framed through reinforcement learning. Often, the agent only sees reward after solving the task from start to finish, which makes learning difficult. A solution trajectory might have to take many correct actions or traverse bottlenecks, like going to the table or picking up an apple before ever seeing reward. In short, learning from sparse rewards for complex tasks is not sample efficient. But if we notice what's actually involved in solving a high-level instruction, we can naturally break down the problem into low-level instructions. And if we frame these instructions as getting us closer and closer to solving the high-level task, we can then densify the rewards and provide more signal for learning. Concretely, this work asks the question of whether we can use the principle of abstraction in language to guide exploration. We frame our problem as reward shaping, where an agent receives intermediate rewards for relevant behaviors like those shown here. Each of these lower-level instructions can themselves be solved by a primitive action set. And reward shaping allows us to be flexible in how we incentivize exploration. Prior work has required that high-level instructions exactly factorize into a sequence of low-level behaviors, or that these decompositions are explicitly provided. We don't make these assumptions in order to be more flexible. For example, say we need to complete primitive actions between low-level behaviors to weave them together. Additionally, we only require a general set of low-level instructions and not an explicit list for every high-level task. Other work has looked at language-based shaping without taking advantage of abstraction, and an orthogonal line of work looks at improving exploration through intrinsic motivation and curiosity. We'll now formulate our problem more precisely using a grid world, where the black triangle represents the agent. We consider an augmented MDP consisting of states, like the grid here, a primitive action set, as listed, and transition and sparse reward functions that are conditioned on a high-level goal in the set G. We also assume access to a set of low-level instructions, G sub L, such that every high-level instruction is supported by some low-level instruction. And we'll go through an example in a moment. We assume a finite horizon H and a discount factor gamma. Our goal is to transform the reward function R into a function R prime to reward subtask-based exploration. Now, as an example, our high-level instruction set might contain instructions like go to the red ball and then to the blue ball, or put the red ball next to the blue ball. The low-level instruction set might contain go to the red ball and go to the blue ball. Now, the task put the red ball next to the blue ball can be solved by completing go to the red ball, followed by a primitive action, pick up, followed by the rest of the trajectory. ELA would assign reward after each low-level instruction is completed. We'll now look at an overview of ELA as a whole. In a standard RL episode without shaping, an agent would either fail and get no reward, or succeed and get the full reward. But with ELA, we check at every time step if the agent has completed a relevant subtask, and if so, the agent gets a small subtask reward. If the agent later fails to solve the task, they get no additional rewards. But if it does solve the task, it gets the balance of the rewards. Let's look at subtask completion in more detail. We need a way to determine which subtasks have completed, and whether they are relevant to the high-level task. To do this, we use a termination classifier trained on an expert annotated dataset of termination states of subtasks. To answer the second question, we use a relevance classifier that determines online whether a subtask is relevant to a high-level instruction. This classifier uses a relevance dataset collected completely online. The dataset gets updated whenever the agent succeeds at a task. We'll now discuss each module in turn. So first, the termination classifier. The low-level termination classifier predicts whether a particular low-level instruction has terminated at a given time step. We assume access to a set of positive and negative examples of termination states provided by a human annotator or collected automatically. The architecture that we use relies on both visual state information and the low-level instruction, and uses a film layer to fuse the inputs. Now, given that some subtask is terminated, we next ask if it is relevant before providing an intermediate reward, and we'll now discuss the relevance classifier. The mapping from high-level goals G to the set of relevant low-level instructions in the power set of G sub L is initially unknown. One example mapping is from the high-level instruction open the red door to the set pick up the red key and go to the red door. We represent such a mapping as a binary predictor of whether a pair of high and low-level instructions is relevant. And we use a Siamese network to make these binary predictions. Let's now discuss how we collect data online to train this relevance classifier. Consider this trajectory of an agent exploring and then solving the task, put the red ball next to the blue ball. A trajectory like this might happen early on in training. It's suboptimal, but it solves the task. We record the completed low-level tasks and save in the relevance dataset D. As we can see, there are some irrelevant subtasks that also get recorded. As learning progresses, we may encounter this high-level task again and traverse another set of low-level tasks. We can perform a simple deduplication procedure to improve the dataset entry. Specifically, we can intersect the old and new decomposition estimates and save the result in D. This estimate becomes just the truly relevant low-level tasks. Go to the red ball and go to the blue ball. We can then balance the dataset D and optimize a cross-entropy objective to train the relevance classifier. To summarize so far, we have a way to determine when the agent completes relevant low-level tasks. We'll now discuss how to transform the reward function to incentivize completion of these low-level tasks. Specifically, we provide a small bonus lambda whenever a relevant low-level task terminates. But if we leave it at that, the agent will get distracted by the subtasks and cyclically complete them, accruing more and more reward. We can avoid this problem and problems like it, where subtask bonuses might change what the optimal policy is, via two design choices. First, we cancel intermediate rewards in successful trajectories whenever the agent solves the task. Second, we limit return in unsuccessful trajectories by tuning lambda, so an unsuccessful trajectory can never get more reward than a successful one. And we find a bound for lambda that accomplishes this, which also helps guide hyperparameter tuning. This bound can be improved with minimal knowledge of the environment. Please see our paper for more details. We'll now discuss how Ella performs in several baby AI environments. We choose 6 high-level tasks paired with subsets of 4 low-level tasks, and we show some example task instances here. The red triangle represents the agent. We select our task pairs to differ on several axes: sparsity of the high-level task, similarity of the low and high-level tasks, and compositionality of the high-level tasks. We'll now take a look at the performance of Ella across environments that vary along these 3 axes. So first, sparsity. We'll start with put next room. where the task is to put an object next to another object. The low-level task is going to an object. We compare three algorithms: PPO without shaping, PPO with shaping based on Learn, another language reward shaping method, and PPO with Ella-based shaping. Ella induces gains in sample efficiency, and we can compare this to a two-room version of this task. Relative gains by Ella are larger for the bigger environment because reward signals are more spatially sparse, and so spatial subgoals, such as going to relevant objects, help the agent navigate. Another degree of sparsity comes from bottlenecks. For example, in the unlock environment, the agent must pick up a key of the right color before it can successfully open a colored door, and random exploration rarely passes such bottlenecks. With picking up keys as the low-level task, Ella quickly learns to correlate the right keys with opening the colored door. This allows agents to navigate these bottlenecks and improve sample efficiency. Next, we look at low and high-level task similarity. In the combo environment, tasks consist of multiple types of instructions, like the ones listed here. The low-level task of going to an object is similar to a lot of the high-level tasks. So the exploration that Ella encourages does not hurt, but it does not help much, because the low-level tasks are similar to the high-level tasks. We also test Ella on compositional high-level instructions. The open and pick tasks require opening a door and picking up an object. Here we have two low-level instruction families that relate to opening doors and going to objects. The relevance classifier becomes harder to learn in this case with more compositional instructions, but we still see a boost in sample efficiency. Scaling up in the sequence task, we have over 1.5 million compositional and diverse instructions. We see marginal gains from Ella, although the exploration problem remains very difficult. This wraps up our experiments for environments across the three axes. We can do further analysis on the online relevance dataset and classifier to get transparency into Ella. First, let's look at the put next task. Over in RL run, decompositions in the relevance dataset get more targeted, as we see in the graph on the left, and the classifier becomes very accurate, as we see on the right. This occurs as the policy improves in terms of average return. Next, let's look at the sequence task, where Ella has only marginal gains. Ella incentivizes general subtask completion, as evidenced by the growing decompositions, but the decompositions are noisy, so the relevance classifier does not get very accurate. It's difficult to offer targeted bonuses in this case. Scaling up to highly compositional instructions, like those that might appear in real human-robot interactions, remains a challenge, but we do believe that abstractions will be a key to learning such systems. To summarize, Ella is a framework for abstraction-based reward shaping for instruction-following agents that guides exploration towards relevant subtasks. We're excited about the idea of scaling up to more natural interactions between humans and robots. Thank you, and please check out our paper for more details.